In this section, we will talk about the most commonly used technique for biasing, current source, and current mirror. Biasing in integrated circuit design is based on the use of constant current sources. On an IC chip with some amplifier stages, a constant DC current, called a reference current, is generated at one location and is then replicated at various other locations for biasing the various amplifier stages through a process known as current steering. This approach has the advantage of the effort expended on generating a predictable and stable reference current, usually utilizing a precision resistor external to the chip or a special circuit on the chip, need not be repeated for every amplifier stage. Figure 7.1 shows a circuit of a simple MOS constant current source, where Q1 and Q2 are matched MOSFETs. Their gates are connected, and the gate and drain of Q1 are short-circuited to form a current mirror. For proper operation, the output terminal, that is, the drain of Q2, must be connected to a circuit that ensures that Q2 operates in saturation. The heart of the circuit is transistor Q1, the drain of which is shorted to its gate, thereby forcing it to operate in the saturation mode with the drain current equation, where we have neglected channel length modulation. The voltage source VDD supplies the drain current of Q1 through resistor R, which in most cases will be outside the IC chip. Since the gate currents are zero, we can get the ID1 like this equation, where the current through R is considered the reference current of the current source and is denoted IREF. Equations 7.1 and 7.2 can be used together to determine the value required for R to generate a given IREF. Now consider transistor Q2. It has the same VGS as Q1. Thus, if we assume that it is operating in saturation, its drain current, which is the output current I/O of the current source, will be this equation, where we have neglected channel length modulation. Equations 7.1 and 7.3 enable us to relate the output current I/O to the reference current IREF as the following equation. This is a simple and attractive relationship. The special connection of Q1 and Q2 provides an output current I/O that is related to the reference current IREF by the aspect ratios of transistors. In other words, the relationship between I/O and IREF is solely determined by the geometries of the transistors. In the special case of identical transistors, I/O equals IREF. The circuit simply replicates or mirrors the reference current in the output terminal. For this reason, the circuit composed of Q1 and Q2 is called a current mirror. Note that the term is used regardless of the ratio of device dimensions. Figure 7.2 depicts the current mirror circuit with the input reference current shown as being supplied by a current source for both simplicity and generality. The current gain or current transfer ratio of the current mirror is given by equation 7.4. We next consider the effect of VO on I/O. In the description above for the operation of the current source of figure 7.1, we assume Q2 to be operating in saturation. This is essential if Q2 is to supply a constant current output. To ensure that Q2 is saturated, the circuit to which the drain of Q2 is to be connected must establish a drain voltage VO that satisfies equation 7.5, or, equivalently, in terms of the overdrive voltage VOV of Q1 and Q2, like equation 7.6. In other words, the current source in the current mirror will operate properly with an output voltage VO as low as VOV, which is a few tenths of a volt. The minimum voltage VC-SMIN required across a current source or current mirror for its proper operation is an important characteristic parameter of the current source and the current mirror. Given that for modern CMOS technology, VDD has become as low as 1 volt or so, it is imperative that VC-SMIN be as small as possible. For the current source in figure 7.1 and the current mirror in figure 7.2, VC-SMIN is equal to VOV of Q1 and Q2 For the mirror in figure 7.2, we see that the output current will be at its nominal value of equation 7.7. At the value of VO that makes Q1 and Q2 have the same VDS, that is, VO equals VGS. As VO deviates from this value, IO will deviate from a nominal value by IO, like equation 7.8, where RO2 is the output resistance of Q2, and where VA2 is the early voltage of Q2. Equations 7.7, 7.8, and 7.9 can be used to find I/O at an arbitrary VO that is greater than VOV, as equation 7.10. This analysis is illustrated graphically in figure 7.3, which shows I/O versus VO. Note that this is the ID minus VDS characteristic curve of Q2 that corresponds to VGS2 equals VGS. Finally, observe from equation 7.9 that the output resistance of the mirror RO2 is proportional to the early voltage of Q2 VA2. Since for a given process technology, VA2 is proportional to the channel length of Q2, to obtain a high output resistance, we normally give the mirror transistor Q2 a relatively long channel. Figure 7.3 shows the output characteristic of the current source in Figure 7.1 and the current mirror of Figure 7.2. The output current I/O is affected by the early effect. When the output voltage VO increases, the output current I/O will also increase according to the slope of the characteristic curve in the saturation mode. Next, we will introduce example 7.1. Given VDD is 3V and using IREF is 100 μA, design the circuit of Figure 7.1 to obtain an output current whose nominal value is 100 μA. Find if Q1 and Q2 are matched and have channel lengths of 1 micrometer, channel widths of 10 micrometers. VT is 0.7 V, and Kn is 200 μA per V square. What is the lowest possible value of VO? Assuming that for this process technology, the early voltage VA is 20 V per μm, find the output resistance of the current source. Also, find the change in output current resulting from a plus 1 V change in VO. Thus, VOV is equal to 0.316 V, and VGS is equal to VT plus VOV equals 0.7 plus 0.316, close to 1 V. And we can calculate R is equal to 20K ohms from this equation. VOM equals VOV close to 0.3 V. Now we can find the output resistance of the current source, RO2. For the transistors used, L is 1 micrometer. Thus, VA is equal to 20 V, and RO2 is 0.2 megaohms. The output current will be 100 μA at VO equals VGS is 1 V. If VO changes by plus 1 V, the corresponding change in I/O will be calculated from this equation. Delta I/O is equal to 5 UA. Figure 7.4 shows a simple current steering circuit. Here Q1 together with our determine the reference current IREF. Transistors Q1, Q2, and Q3 form a two-output current mirror, where the relationship between IREF I2 and I3 is determined by the geometries of the transistors. To ensure operation in the saturation region, the voltages at the drains of Q2 and Q3 are constrained as follows, or equivalently as this equation, where VOV1 is the overdrive voltage at which Q1, Q2, and Q3 are operating. In other words, the drains of Q2 and Q3 will have to remain higher than minus VSS by at least the overdrive voltage, which is usually a few tenths of a volt. Continuing our discussion of the circuit in Figure 7.4, we see that current I3 is fed to the input side of a current mirror formed by PMOS transistors Q4 and Q5. This mirror provides the following equation, where I4 equals I3. To keep Q5 in saturation, its drain voltage should be satisfied as this equation, where VOV5 is the overdrive voltage at which Q5 is operating. The constant current I2 generated in the circuit of Figure 7.4 can be used to bias a source follower amplifier like the one implemented by transistor Q6 in Fig. 7.5a. Similarly, the constant current I5 can be used as a load for a common source amplifier like the one implemented with transistor Q7 in Fig. 7.5b. Figure 7.5 application of the constant currents I2 and I5 generated in the current steering circuit of Figure 7.4, where A, constant current I2 is the bias current for the source follower Q6, and B, constant current I5 is the load current for the common source amplifier Q7. In the circuit of Figure 7.4, while Q2 pulls its current I2 from a circuit not shown in Figure 7.4, Q5 pushes its current I5 into a circuit, not shown in Figure 7.4. Thus, Q5 is appropriately called a current source, whereas Q2 should more properly be called a current sink. An IC normally needs both current sources and current sinks. The difference between a current source and a current sink is further illustrated in Figure 7.6, where VC-SMIN denotes the minimum voltage needed across the current source, or sink, to operate properly. Figure 7.6, where A shows a current source, and B shows a current sink. The basic BJT current mirror is shown in Figure 7.7. It works in a fashion very similar to that of the MOS mirror. However, there are two important differences. First, the non-zero base current of the BJT, or equivalently, the finite beta, causes an error in the current transfer ratio of the bipolar mirror. Second, the current transfer ratio is determined by the relative areas of the emitter base junctions of Q1 and Q2. Figure 7.7 shows the basic BJT current mirror. Consider the case of beta sufficiently high that we can neglect the base currents. The reference current IREF is passed through the diode-connected transistor Q1 and thus establishes a corresponding voltage VB, which in turn is applied between the base and emitter of Q2. Now, if Q2 is matched to Q1, or more specifically, if the EBJ area Q2 is the same as that Q1, and thus Q2 has the same scale current IS as Q1, then the collector current of Q2 will be equal to that of Q1. That is, IO is equal to IREF. For this to happen, however, Q2 must be operating in the active mode, which in turn is achieved as long as the collector voltage VO is 0.3 V or so higher than that of the emitter. To obtain a current transfer ratio other than unity, say M, we simply arrange that the area of the EBJ at Q2 is M times that of Q1. In this case, IO is equal to M times IREF. In general, the current transfer ratio is given by equation 7.17. Alternatively, if the area ratio M is an integer, we can think of Q2 as equivalent to M transistors, each matched to Q1 and connected in parallel. We consider the effect of finite transistor beta on the current transfer ratio. The analysis of the case in which the current transfer ratio is nominally unity, that is, the case in which Q2 is matched to Q1, is illustrated in Figure 7.8. The key point here is that since Q1 and Q2 are matched and have the same VB, their collector currents will be equal. The rest of the analysis is straightforward. A node equation at the collector of Q1 yields the following equation. Finally, since IO equals IC, the current transfer ratio can be found as equation 7.18. In Figure 7.8, we label the currents in each branch of the BJT circuit to analyze the BJT current mirror when beta is a finite value. Note that as beta approaches infinity, IO/IREF approaches the nominal value of 1. For typical values of beta, however, the error in the current transfer ratio can be significant. For instance, beta equals 100 results in a 2% error in the current transfer ratio. Furthermore, the error due to the finite beta increases as the nominal current transfer ratio is increased. We encourage you to show that for a mirror with a nominal current transfer ratio M, that is one in which IS2 is equal to M times IS1, the actual current transfer ratio is given by equation 7.19. In common with the MOS current mirror, the BJT mirror has a finite output resistance rho, as shown in equation 7.20, where VA2 and RO2 are the early voltage and the output resistance, respectively, of Q2. Thus, even if we neglect the error due to finite beta, the output current IO will be at its nominal value only when Q2 has the same VC as Q1, namely, at VO equals VB. As VO is changed, IO will correspondingly change. Taking both the finite beta and the finite rho into account, we can express the output current of a BJT mirror with a nominal current transfer ratio M as equation 7.21, where we note that the error term due to the early effect is expressed in a form that shows that it reduces to 0 for VO equals VB. As in the MOS case, the basic BJT current mirror can be used to implement a simple current source, as shown in Figure 7.9. Here the reference current is as equation 7.22, where VB is the base emitter voltage corresponding to the desired value of IREF. For matched transistors, the output current IO is given by equation 7.23. The output resistance of this current source is RO of Q2, like equation 7.24. To generate bias currents for different amplifier stages in an IC, the current steering approach described for MOS circuits can be applied in the bipolar case. As an example, consider the circuit shown in Figure 7.10. The DC reference current IREF is generated in the branch that consists of the diode-connected transistor Q1, resistor R, and the diode-connected transistor Q2 as an equation 7.25. Now, for simplicity, assume that all the transistors have high beta, and thus that the base currents are negligibly small. We will also neglect the early effect. The diode-connected transistor Q1 forms a current mirror with Q3. Thus, Q3 will supply a constant current I1 equal to IREF. Transistor Q3 can supply this current to any load as long as the voltage that develops at the collector does not exceed VCC minus 0.3 V. Otherwise, Q3 would enter the saturation region. To generate a DC current twice the value of IREF, two transistors, Q5 and Q6, each of them matched to Q1, are connected in parallel. The combination forms a mirror with Q1, so that I3 is equal to 2 times IREF. Note that the parallel combination of Q5 and Q6 is equivalent to a transistor with an EBJ area double that of Q1, which is precisely what is done when this circuit is fabricated in IC form. Transistor Q4 forms a mirror with Q2. Thus, Q4 provides a constant current I2 equal to IREF. Note that while Q3 sources its current to parts of the circuit whose voltage should not exceed VCC minus 0.3 V, Q4 sinks its current from parts of the circuit whose voltage should not decrease below minus V plus 0.3 V. Finally, to generate a current 3 times IREF, 3 transistors, Q7, Q8, and Q9, each of which is matched to Q2, is connected in parallel, and the combination is placed in a mirror configuration with Q2. Again, in an IC implementation, Q7, Q8, and Q9 will be replaced with a transistor having a junction area 3 times that of Q2. Figure 7.11 shows a bipolar current mirror with a current transfer ratio that is much less dependent on than that of the simple current mirror. The reduced dependence on beta is achieved by including transistor Q3, whose emitter supplies the base currents of Q1 and Q2. The sum of the base currents is then divided by beta 3 plus 1, resulting in a much smaller error current that has to be supplied by IREF. Detailed analysis is shown on the circuit diagram. It is based on the assumption that Q1 and Q2 are matched and thus have equal collector currents IC. A node equation at the node labeled X gives the following equation. Since IO is equal to IC, the current transfer ratio of the mirror will be expressed as equation 7.26, which means that the error due to finite beta has been reduced from 2 over beta in the simple mirror to 2 over beta square. A tremendous improvement. Unfortunately, however, the output resistance remains approximately equal to that of the simple mirror, namely RO. Finally, note that if a reference current IREF is not available, we simply connect node X to the power supply, VCC, through a resistance R. The result is a reference current given by equation 7.27. Figure 7.12a shows a MOS current mirror bias with a DC input current ID1 and fed with a small signal input current 2. Note that VGS and ID2 are the resulting DC quantities, while VGS and IO are signal quantities. Although we are not showing the circuit to which the output terminal is connected, we are assuming that the voltage at the drain of Q2 exceeds the minimum required to keep Q2 in saturation. Figure 7.12b shows a small signal equivalent circuit model of the current mirror. In the following, we determine the value of the model parameters. Figure 7.12 shows the small signal parameters of the MOS current mirror as a current amplifier. Replacing Q1 and Q2 with their small signal models, the equivalent circuit can be redrawn in Fig 7.12c. Notice that the control current source GM1 VGS appears across its control voltage VES, and thus can be replaced with resistance 1 over GM1, as shown in Fig 7.12d. For the latter circuit, we can obtain equations 7.28 and 7.29, where VGS can be replaced as this equation. Thus, we can get the short circuit current gain A's as equation 7.30. Substituting for GM1, 2 equals Ncox W/L VOV, where VOV is the overdrive voltage at which Q1 and Q2 are operating, yields a short circuit current gain as equation 7.31, which is equal to the DC or large signal current transfer ratio, except for a small error factor represented by the quantity in the square brackets. We conclude that the current mirror is an excellent current amplifier. It has a relatively low input resistance, 1 over GM1, a relatively high output resistance, RO2, and a gain determined by the aspect ratios of the MOSFETs.